Cool. Welcome everyone to week 18 of Intro to Quantum Computing. I'm gonna wait another couple minutes before getting started on the actual material since we are at half typical numbers. But I'm gonna go through the usual rigmarole, and if you have any questions, feel free to ask those now, especially this week's topic, I guess, is kind of one of the first kind of common quantum, I guess not really algorithms, like quantum protocols that we'll be covering this semester. There's a few kind of classics, quantum teleportation being the other half of what we covered in, or I believe you may have also covered it in lecture this week, but in lab we're just going to be doing the superdense coding part, and also our attendance quiz code can be found in the bottom right hand corner of every slide as usual. But yeah, there's a few kind of very standard protocols that are just good to kind of know what they are. Yeah, this week the Canvas attendance quiz is what level of difficulty you feel the work in this course is generally. I don't actually know what scale they have it on, but like how difficult it is. But yeah, cool. And then also we have our pre-lab Zoom feedback, which I will start. I'll wait to start it. So if you guys have any kind of questions for this week's material, please note them now so I can work through them on the slides, because we don't really have slides for this week. It's all going to be the lab content in quantum experience. So we will be going away from the slides pretty quickly. Oh, okay, cool. Cool. So I have not gotten any questions thus far, but just to give you an overview of the material we'll be covering this week. Oh, and I'll start the Zoom poll in I'll give us till 5 past the hour, because that's standard. At least at MIT, we call it MIT time. We start 5 past, just because we're a little under. But this week we will be implementing superdense coding on Qiskit, which has, I guess, 3 steps. We have our state preparation, our state encoding, and then our state decoding. And this operates in I guess commonly the way we're going to be doing it is describing it as a 2-party protocol in its entirety, but often it is denoted kind of more as a 3-party protocol where there's Alice, Bob, and Charlie, which you will note where Charlie comes in. If you see that, even on some of IBM's documentation, they have a 3rd party that you might be unfamiliar with based on how we are going through in this course. Also gotten a question from Michael, if the Discord will be deleted after the course ends. I don't know. That's a question that would be best to ask student at Qubit by Qubit, which is the moderators, or the people in charge by qubit.org, I think it's this. And because I don't I have no control over anything in this course other than what I teach in lab pretty much. I have complete control over what slides I choose to use, and the lab content. We do have standards that we have a head TA that creates, but we are allowed to vary them. Also gotten a question from Zena if there are any other courses to enroll in after this one. I don't know if there's going to be a more advanced topic covered by like the coding school or like by like the qubit by qubit program. I think they're kind of planning on keeping it to be this 1 year thing. They also have like a summer camp version, but it'll all be kind of the same material, I think, because it is kind of just like a survey of basic quantum. I think the like my take, I can also ask if there is a plan for a more advanced version of the course, but you could check on like EDX, like, or like edX, I don't know how you say it, like that. There's a lot of quantum mechanics, like a basic quantum mechanics course. If you're not, if you don't already have like a quantum mechanics background, could be very useful, I guess. There are like, I know, so I'm going to give like potentially incorrect information because I do have access to like the MIT internal version of EDX. So there is like the course that is taught by Ike Chuang, who wrote, let me grab it, wrote Mike and Ike, like quantum computation and information. He has a course that's taught at MIT and it's available through MITx. I don't know if it's available on like edX. It might be on YouTube. There's also a course that I really liked, and I'm going to start the pre-lab Zoom poll since we're now at about normal numbers. We do also have, there's also a course by, it is a graduate level kind of advanced course. It's atomic molecular and optical physics by Wolfgang Ketterle. And that's on YouTube. It's also like through like MIT like OpenCourseWare. Yeah, MIT OpenCourseWare is actually like a great option for more advanced material. This like, so atomic molecular and optical physics is kind of like the basis of quantum computation, like all of the original protocols for this like superdense coding. Oop, I am like, oh, such disaster. The original protocols for superdense coding and quantum teleportation, and I think possibly all of them, I don't want to make a super strong claim, are implemented like optically with like entangled photon pairs. So I like, this is like it is a graduate level course, not an undergraduate level course. So you do need a basis in linear algebra for it. You also should probably have like a pretty, like most quantum courses assume you have a decently strong background in differential equations. So you could also probably find, if you want a mathematics background for them, like most quantum courses are built for a more like mathematically heavy background than this one, because they're meant for like this one's meant for graduate students. So you've taken all of like the calculus sequence and linear algebra and differential equations, possibly like partial differential equations at some point in undergrad. So they kind of assume you know a lot of this material already, and so that it makes a lot of the formalism a lot easier if you do know that. Yeah, I would recommend like just checking out online course options, I guess, if you want to get like more of a, like if you don't have the mathematical basis will serve you extremely well no matter what field you go into. Like linear algebra will serve you in honestly anything, but any kind of computer science, it is like fundamental, and any like engineering degree it's very important. And in most fields now kind of require some decent understanding of linear algebra because they require some decent understanding of like how to program. So it's all like very worthwhile. You'll never regret having some knowledge. Yeah, okay. Cool. So I'm getting a lot of 4s in the pre-lab Zoom feedback. So I will try to take that into account. I know this protocol is a little bit confusing, and I feel like the name of it is a little bit loaded. It makes it sound like you're programming something. They call it coding, not like encoding, I guess. Like, I don't know. I find it a bit weird what they call it. But yeah, okay. I've also gotten a couple more questions, I guess, about like, I guess we're not super close to the end of the course, but we are approaching. Sorry, a question from Zena: if we want to do a master's degree in quantum computing, you need to have a bachelor's degree in physics. No, I don't have a bachelor's degree in physics. I have a bachelor's degree in electrical engineering. I don't know a ton of people outside of electrical engineering or physics that are in the field, but like they exist. I know people like, I know of people like, right? I do personally know some people that were in like very unrelated fields, like English, and just had to do like a lot of prep work. They typically like would take undergraduate level courses like in other areas, like in physics and math, to like be up to speed. I have one friend that was in environmental science and switched to like pretty much physics. Like she's under electrical engineering, but like does stuff very close to physics, like a very applied physics work in grad school, but it is a little bit rough. I'd recommend like making sure to take like those of you in high school, a lot of things don't matter a ton, but some things like taking like basic mathematics sequence, like all of calculus and differential equations, is really, really important. And then taking the full quantum mechanics sequence at whatever university you're at, and the full electrodynamic sequence is like very important and will serve you very well. Everything else, like the like experimental physics courses, are kind of useless. Like modern physics is often kind of like it covers a survey of topics that is nice to have, but you don't need a lot of the more special topics when going to graduate school. Like you can take the special topics you want at that point, or you're probably not going to deal with them unless you specialize in that area. I also gotten a question from Elon if it is recommended to take an intro to quantum computing course in college if you understand all the content in this class. This class is overall aimed like so that it is accessible to and compatible with the background that a high school audience would have. So I would still recommend taking a like undergrad level or like grad level. I guess I don't know if there's any undergrad level quantum courses that I know of that are like full courses. Like our lecturer Amir he teaches a undergrad level intro to quantum course here, but that's just like a 1 month thing over like it's called independent activities period. It's like just a weird like 1 month during the winter where you can take things that are interesting to you but aren't like full-fledged courses. You will do a lot more math and a lot more problems in a full like undergraduate or especially graduate level quantum computing course. So I'd still recommend taking it if you are at the point in your life where you're considering that. Like it's definitely like a undergraduate level like course in quantum computing. I would anticipate would probably take up like 10-15 hours a week at least. And I don't think this is quite like we have 2 hours of lecture a week. And yeah, so I'd definitely recommend taking a full quantum course if that is like a field, if it is a field you're interested in going into. Okay, I don't want to go too much into like college advice, so I'm gonna answer like the 2 questions I have on my screen now, and then we'll move on. And we can answer. I'm very happy to answer more at the end. But I got a question from Dennis about how important the university that you go to is for working in quantum. I have no idea. I think the amount of funding you'll have for research at your university will depend heavily on like the university, like what like, and to some large extent, like funding is correlated with like name recognition. But if you are like the professor you work with matters a lot more than the university you go to. And the work that you do matters like probably I'd say equally as much to the professor you work with. It will be a lot easier to do good work if you are working with a professor who like is well established, knows how to run a group well, has like good understanding of like where the field is going and what like a good approach is to different problems, what's interesting to go into. But you don't have to like be working with a professor that like is well known in the field for that to be the case. They can be like very like good at being an advisor or a new like most like big professors like big name professors were first students for their advisors, so like their advisors had no name recognition at the time that they started working with them. So it all kind of depends. I'd say like a university matters a lot if you are like for funding and if you do not have a successful PhD or a successful research career like during your PhD. It matters much less if you do like very good work. Like your name matters a lot more than your university's name when it comes to getting a job, especially if you're not going into academia. So, and like people from like people that are doing PhDs here in like at MIT in quantum in like any field, like they're from all over the world and all kinds of universities all over the world. Like I know tons of people that went to liberal arts universities for undergrad that barely had a physics department. So it really depends on like you won't like things, a lot of doors are opened and are made much easier if you go to a university with like a brand name recognition. But the doors like most things like with extra effort are still like perfectly available. And a question from Amy, if I'd recommend retaking math or science classes that could be stuff with AP credit. So I will answer this because I skipped every single math and science course I could with like high school credit, and I have zero regrets. They cover the exact same material. I know people that took them and like were just miserable because they like a lot of these like kind of intro like undergraduate level courses. So I know a lot of guys are like seniors in high school. Like a lot of these courses are just like the exact same material, but a lot of times more work. And so just, oh, sorry, I'd recommend retaking math and science courses that could be skipped with an AP credit or like high school credit, dual credit, whatever. So like your intro calculus, intro physics, I'd recommend, like I skipped them and I recommend skipping them. I don't think I would have gotten anything out of them. One of my friends who is very good at math took like Calc 1 or Calc 2 or something at our university, and it just like destroyed, like her semester was just like taken up by that one course because there was just so much like busy work, and she like got like an A minus, like a B plus or something in it, and she was just like, why did I do this? Like she knew the material too, she just like, it was just a disaster. So I'd recommend not doing it. I think your time is much better served taking more advanced courses, and if there are holes in your knowledge, like you will identify them very easily with the more advanced courses because you'll cover a topic and you'll be like, oh, I don't remember this. So since everything kind of builds up, unless you feel shaky with the material, I'd recommend just moving on. It will cover the same thing. So yeah. Also, you don't have to do calculus by hand like ever in real life. Like you put it into like Mathematica, like you have to know like exponentials. Like that's the only thing you have to know, and like sines and cosines, like you should be able to like do that off the top of your head. But like all these complicated equations, like you'll mess them up anyway if you try to do them by hand. Like I'm pretty sure I've messed them up on slides trying to do them by hand. So like it's very good to like learn thoroughly doing it by hand, but you don't need to do 8 million problems of like basic calculus. Like there's some like useful integrals that are like fun to know, but yeah. Okay, so with that, I will switch to my computer so we don't go to overtime. I know like we are getting towards like decision making time. Sorry, my Zoom has decided it wants to install my an audio sharing application. I don't know what's happening. Right? Okay. Is this, you guys can see my screen, I hope. Oh, is something cool? Okay, you guys can still hear. Cool. Yeah. Okay. So I've scrolled down from this, unfortunately, but here is beginning of this week 18 lab where we're going to be doing Superdense coding. So as usual, the first step is always to import all of our Qiskit things we need. So from our Qiskit package, we need our quantum circuit to actually create the circuits, our execute to run the circuits to provide all the functionality for different types of analysis we want on it, and then air, which is our backend, which is how we sync up to IBM servers to actually run this. And then we have our visualization as well. So I'm going to run that. And remember, again, that when there's an asterisk here, that means it hasn't finished running yet. So if you try running a cell that's below it and it doesn't run, or it gives you an error, that could be why. Like you have to make sure it completes. And the quantum experience has been running more slowly lately. So that is a thing to be mindful of if you run into issues like that. So we've covered this a bit in lecture, but the idea for what we're doing with superdense coding is if we have a message that is like this, maybe 8 bits, and we want to send it to someone, if we want to send 8 bits of information, we have to, like for classical bits, we have to physically send 8 single bits of information. However, with superdense coding, also originally called hyperdense coding, I actually found out recently, is a quantum protocol that uses quantum bits rather than classical bits. And due to the entanglement of your quantum bits with each other, from the sender to the receiver, you can encode 2 classical bits of information in each single qubit you send over, because there is like a kind of key qubit that you already have at your receiver point. So it's a bit like you still are using 2 qubits in the end, but you don't have to send these 2 qubits from your sender to your receiver. And I'll explain like why that could be useful in just a second when we get to we have a little image that kind of explains it. So the protocol starts out or requires using 2 qubit entangled states. So the Bell states we've previously used, this phi plus, phi minus, psi plus, and psi minus. These are the same states we covered last week. We created this phi minus last week, and we created phi plus a couple of weeks ago. Is it not good resolution? I don't know if it's because of my streaming. Is everyone else having this issue? I optimized it for video clip this time because I do have to upload this to the YouTube channel, but I can try unoptimizing if you guys are, if many of you are having issues seeing. Okay. I'm getting some, it seems all right. I'm sorry, Clark, your Wi-Fi might just be a little bit slow if it's not on my end. What I'm gonna try to do is I'll still get rid of this first of all, so it's easier to see. And I can maybe zoom in just a smidge. That didn't really help. Maybe that helped. Especially because you guys, so I know some of you are looking on phones. Hopefully this is better. Sorry, I always forget to zoom in. Okay, cool. I fixed it through doing very little. But yeah, definitely always ping me if you can't see it super well. I can see it very well because it's on my computer, obviously. So I always forget that when it goes through the whole process, it gets harder to see. maybe if we were using super dense coding, it'd be better. It wouldn't actually, but like, it maybe could help. So in super dense coding, we're going to be using these 4 states that to start with, and this kind of just goes through the 2 qualities of these 4 Bell states can have, which are the parity and the phase, and that's what distinguishes these four states. And the question that we're kind of asking this time is how many bits of information can each of these Bell states carry? So you can see there's 2 2-qubit states, like in kind of encoded in each Bell state, and so we do get like, I guess we can store additional information using the entanglement of these 2 states, or these 2 qubits that gives you these 2 possible states. So the protocol that we saw in lecture was 5 steps. We first prepare the state, where in this case, we say that Alice and Bob meet up and split an entangled Bell state. A common description of this is instead of having Alice and Bob meet up, we have a third party, Charlie, that just sends half of the entangled Bell state to each Alice and Bob. So that is another version of the protocol. It's the same idea. It doesn't really matter how you get this entangled state originally. You just need to get like one part of an entangled state. And then if Charlie's involved, then you can just ship it to them when they're already far away. If they have to go close together, like obviously like sorry, not obviously, that is a bad thing to say. You do need to be close together. You need to have your states close together to entangle them. You need to have some ability to transfer like energy selectively between your 2 states. So there are protocols that kind of like distribute entanglement using photons, but photons are packets of energy, and you are sending like you can send your entangled photons and then transfer that entanglement to like a commonly like a nuclear state, but that still requires like that energy being transferred. It's still something is being transferred to them. You don't just have like, you can't just create an entangled state without having both parties for your entangled state like close by. So like both qubits have to be in each other's vicinity, or you need to have some mediating. I don't know if you can actually do a mediating interaction to just like, you can distribute entanglement once you've created it, but in general, like entanglement operations are like very sensitive and very difficult to do, while like 2-qubit gates are difficult to do with high fidelity. And so typically your qubits will be very close together, whether they are in Alice and Bob's hands or in Charlie's hands. So after that, the actual, when we want to actually send our message, we have to encode the state we want in our qubit. And we have 4 options for what we can encode. Then we can transmit the qubit to Bob, who will then decode it using his like qubit that is entangled with Alice's original, or with Alice's qubit. So this orange qubit is the modified, like encoded qubit, but it is the same one that we started with over here. And then the final state we end up with is created by kind of like doing the backwards, like the inverse gate sequence, which I'll go into in more detail in a second, and then we measure them at the very end. So it's a pretty simple protocol, and I think the going through the different options for what you can encode kind of is the most informative way for how you can get more information sent from one person to another with only a single qubit. And like qubits have pretty high cost to send, I guess, compared to classical bits. We know how to make classical bits very, very easily. Like preparing the state is very easy. But still having to send only a single qubit rather than multiple means that there's a higher likelihood that your protocol will work out. So it is useful to be able to encode more information in a single qubit rather than needing multiple qubits being sent across. There's always some chance of failure, and the net difference between a classical bit versus two classical bits are still probably lower cost than a single qubit to send, but this is a nice advantage to this dense coding protocol. So our first step, so we're going to do our state preparation. So we want to create the same Bell state that we created a couple weeks ago. This is the exact same code. We're including both 2 qubits and 2 classical bits. As you can see down here, qubit 0, qubit 1, and then our 2 classical bits noted here. And the way we're going to do this is the typical way, just reading a Hadamard and then a C0 or CX gate. And then we draw it as usual. This should all seem very familiar. So I will run this. And so once the state is prepared, we're going to, Alice is going to take qubit 0 and Bob is going to take qubit 1. And so as long as we can as long as we don't destroy the entanglement of these qubits through some kind of interaction with them, these qubits will remain entangled no matter where they are. And this is just a note, particularly for your homework, that Charlie often prepares the states and then sends them to Alice and Bob rather than them walking away from each other. Because if you are trying to do some kind of communication protocol, typically you don't have, if you're going to meet up, you can, your entangled qubit is, you can save the state of your entangled qubit in theory, but if you need to get more entangled qubits, it's very inefficient to go back and forth. So you often will have just a third person to provide that. It's the same idea of sharing a private key, kind of. You could meet up and share it, and that's probably most secure, but a lot of times you just have a third party do some mechanism for creating and distributing you could create a private key and store a public key someplace else if you're familiar with cryptography like that. Cool. So now we have Alice and Bob traveling far away. That's kind of unphysical and unnecessary. But if you're doing communication, you're probably far away. But you could do the same protocol from 10 feet away if you wanted to. People do this from opposite sides of the same lab. If they don't have multiple labs, they can send in information between. The third step is encoding the state that you want. And so this is when we're actually going to choose what information we want to send, and then we will send it afterwards. So we have 4 possible Bell states that can exist, and Alice can manipulate her qubit to prepare one of these 4 states. So you get a 2-bit message. So this is where you functionally get your 2 bits rather than just a single bit, but she's sending only a single qubit. And the reason that she can that you can do this, I guess, is because you have this other qubit that's already prepared and entangled with the qubit you're actually manipulating. However, you do only need to do single qubit gates to prepare each of these 4 options. So the listing of the options, or I think I have to scroll down a little bit. I thought we had them listed out. Okay, I'll go through. There's like a nice little page that IBM has on this that I had open at some point. That I'll go through that I think has like just a nice listing, but I'll try to go through like the question and answer version first. So the idea of these 4 states is you need to prepare each of these states somehow by manipulating only Alice's bit, which I guess, are we right indexing or left indexing? So with the way we are writing it here, we are doing right indexing. So it's qubit 0, qubit 1, I believe. And in lecture, we did qubit 0, qubit 1. Most physics textbooks do the least significant qubit is rightmost, but IBM has their, wait, no, sorry, so in lecture, I think I just said the opposite. And most physics textbooks have least significant qubit be leftmost, while IBM has their least significant qubit, i.e. qubit 0, be rightmost. So if you are reading like it's a bit string, then qubit 0 should be your rightmost qubit, because then like you'd raise your qubit 0 to the 0 and get like your smallest bit number, and then like your qubit 1, if it was like a classical bit, you raise it to 2 to the 1, and it's your larger value. But so IBM is using kind of more standard like bit notation, while most physicists kind of go from left to right. As you are writing across a page, you're adding more qubits. And this is the same thing we discussed last week, but it is a bit confusing because there are 2 conventions that we unfortunately like flipped a little bit in lecture. So if you're confused, that is why, that's why these 2 states are flipped compared to lecture. Okay, so if the state we've prepared is this phi plus state, where like we've already created this state without doing anything. And we do have to decide like what each of these Bell state options mean. So like the 4 original Bell states we have, which use the same terminology. So if you're confused, this is different because we are now only talking about a single bit and its state relative to or to a single qubit and its state relative to the other qubits. These are the full states, and then this is a representation of the messages that like correspond to these states. So it's what state you're preparing in Alice's bit to result in sending this message. And I do think there's like a really nice page that I will show you in a second once we go through this. So if we are just sending this 0, 0 state, we've already prepared the phi plus Bell state, and so we don't have to do anything. But if we want to send one of these other messages, we want to switch our state to be one of the other Bell states. So we've already seen how to prepare phi minus last week. Does anyone remember how we did that? It is lower on in the notebook. But like what extra gate we add? As a reminder, the phi minus state has a pi phase relative to the phi plus state. Thank you, Anantha Krishnan. And I'll wait to see if anyone else has thoughts. Okay, Ian agrees. You guys are both correct. But I wanted to see if anyone else would would speak for. Yeah, the gate you need to add is the Z gate, because a Z gate adds a pi phase, and so that's how you create these states. Thank you guys. You guys are very supportive of this answer. I like the increasing number of carets. Yeah, so what we are going to prepare this state, this phi minus state, but then we can also prepare the phi plus and the phi minus state, or yeah, psi plus and the psi minus state. So this is our phi minus state. You can perfectly fine put the Z gate after the entanglement operation. That's the whole way that this protocol works. It doesn't matter what order you put this like Z gate in. So the and this is also like this is fine because the C naught does not affect our qubit 0, because our qubit 0 is our control bit in this case. If that was not the case, then it would be different. But it doesn't matter that we've kind of like split apart our qubits at this point between our C naught and our Z gate. So now we want to create the state psi plus, which is 1 over root 2 with the 0, 1 plus 1, 0 Bell state. And the question now is, what's the difference between the phi plus and the psi plus state? Does anyone remember what the other quality of our 4 Bell states is? I'm not hearing anything. The other quality that I'm looking for is now the parity rather than the phase. So if you remember, the phi plus state was 0, 0 plus 1, 1. Both of those states were even. So 2 zeros, 2 ones, they're both even states, while a 0, 1 and a 1, 0 are odd states, because like you can add like these up. And you get a 1, which is an odd number. You add these up, this is a 1, that's an odd number. While 0 plus 0 is 0, which is even, and 1 plus 1 is 2, which is also even. So this is a different parity than the previous state. So the difference between these two states is that we have done a bit flip operation, or a not operation on qubit 0. Does anyone remember which gate is our not gate? Thank you, Tomas and Elon. Jason, you guys are right on. May have snuck it in a little bit. Thank you, Snahil and Michael. It is the X gate. So all we're doing to flip the parity is doing a bit flip or a not operation, which is just our X gate. And so we can code up this circuit where we've done our same circuit initialization. Oh, and thank you, Jade, as well. We do our Hadamard gate and our C naught gate or our CX gate as usual to create our Bell or standard Bell state. And then once we've separated out our 2 qubits, so this is what Alice is doing by herself. This is, I guess, me. I'll try to like denote what's going on. So I'd say like this is Charlie's part up here. Now Alice and Bob, or I guess we don't have to move away because we just had Charlie send them. Now Charlie sends the qubits to Alice and Bob. And then Alice performs these operations down below. So Alice is just doing this X gate to create this other state. So now that we've done this, I think I actually run it there. Okay, I've run it now. We can actually run this circuit on the QASM simulator. So we're going to add measurement operations. Does anyone remember what this, you can kind of see it in the diagram, I guess, but like, does anyone remember what this sequence means? This bracket 0, 1, bracket 0, 1 in our measurement operation. Oh, I've got a question from Anant Krishnan about how he doesn't understand how applying the X gate after the C naught affects qubit 1. You are correct, it does not affect qubit 1. It is a single qubit gate that only affects qubit 0. However, because the qubits are entangled, the state of qubit 0 impacts qubit 1. That's the whole, like, I guess, unique portion of this. Nice. Oh, and thank you, Jason and Fahim, for answers. You guys are right on. We have our qubits that are going to be spread out into our classical bits, and these are the indices of each. So we have our qubit 0 and qubit 1, which we are then going to measure onto classical bit 0 and classical bit 1. Great. So that is our gate sequence, and now we can run it. And this is the same code pretty much as what we used last week, where we're getting our QASM simulator backend. We are executing a job on the circuit we've created. So this is our Psi plus circuit that we're using the QASM simulator for, and we're doing 1,024 shots. And then we are getting the result function from our job. So we don't necessarily have this job, or this result isn't necessarily populated because it does take some time to run on the simulator. So we can also check like the status of this job while we're waiting on it. And then we are going to get the number of counts from our results. So we've gotten 1,024 shots, so we should get some counts for our different states, and we can plot the histogram of these counts. So we're going to do that. It's a bit hard to read because we're in dark mode. This is our 1, 0 state right here with 51.2% of our shots, and our 0, 1 state here with 48.8% of our shots. So we've successfully created the state that we expect, but what we would like to do is verify the state has the right sign. Does anyone remember how we verified the sign or the phase of the state previously? So Anant Krishna has, we could do a Hadamard gate and before our Z operation to measure in our X basis, and that would tell us what sign we have, which is a way we could do it physically. Which is what we do in lab actually, but we could also do use a state vector simulator, which would make sure that our math was correct and what we thought we were doing is what we're actually doing, although that is a classical approach. I remember I also got a question earlier, if it doesn't matter if the applied gate is before or after the CNOT. Yes, the applied gate, like the extra gate, the whole way this protocol works is it's necessary that it doesn't matter whether it's before or after the CNOT, what effect it has. So that is like a presupposition, and you can like work through the math, putting it before or after, and see that it doesn't affect your end results. And I think that's a good exercise, honestly, if you're interested in kind of working through things by hand. Elon has asked, if you have an unknown quantum state, is there a way to copy that state to another qubit so that you have now 2 qubits with that state? So there is like a no cloning theorem that you can't clone a quantum state. So I would say like it is one of those questions that there is a lot of nuance to it, but I think the simplest, most canonical answer is that no, you can't really do that. You can create, so creating identical particles is actually something that, identical states is something that people are very, very interested in. So if you're working with atoms, like two atoms are identical, two of the same atoms are identical. So that's why people use them for like quantum information. Same with like superconducting qubits. We are creating artificial atoms that could be treated like, or we aim to treat as identical. Creating identical photons is something that there's a lot of like interest and a lot of work that is being done, or like not identical photons, I guess, like entangled pairs of photons. Because it's very hard to have a photon interact with another photon. So creating these entangled pairs is something that people are very interested in doing. And there's a process that people use called spontaneous parametric down conversion they use for it. So that is like a big area. I guess follow-up question, if the quantum state is not exactly the same, but it's very similar. You could, I believe like people kind of do that just by like doing a bunch of, well, it's hard. You can do a bunch of like gate sequences that allow you to transfer like kind of the information you want from one state to another. But like every time you do a gate, you're kind of hurting the coherence of your previous state. So it's a difficult question. There's a lot of research in that area. That is an active research area, trying to copy quantum states. Okay, so back to our protocol. We've now created our state. We've identified ways we could figure out if our state has the correct sign, and we'll create a state with the opposite phase, or like a pi phase relative to this, the opposite sign in the optional content. But to summarize, okay, oh, we do have this table. I thought we had this table somewhere. So depending on what message you want to encode, there is a gate that Alice should apply to encode the message, and the resulting state we get is going to be one of the 4 Bell states. So the state we started out with is this phi plus state. So that's our even parity, like I guess like 0 phase Bell state. And because this is a state that we create by default, that's the one that Charlie creates and sends to Alice and Bob, we don't have to do anything with Alice to create the state. So this I gate is the identity gate. It's just 1 0 0 1. It does absolutely nothing. The only reason like you have it is just to kind of indicate timing, I guess. But it's like you don't actually do anything. It is just kind of like a placeholder saying there could be a gate here. If you want to send 1 0, so this is not in appropriate binary order. So 0 0 is the same as 0. 1 0 is the same as 2. So like this is 2 to the 1 plus 0. If we want to send this state, we've decided that that state is equivalent to having the psi plus state. So that is the opposite parity, like the odd parity version of, but was still with 0 phase. And to do this, you have to do a bit flip operation. So you do a X gate. And I guess actually in this, yeah. Sorry, like, yeah, in this case, actually, so you can see the, we are actually changing the like net state. So all we've done is flip this like 1 1. We flipped, or actually, well, it depends where we put qubit 0. We'll say qubit 0 is this bit and qubit 1 is this bit. I tend to read them backwards because that's what the physics convention is. But the Qiskit convention is very much, this is qubit 0 and this is qubit 1. So we are flipping qubit 0 and getting, putting a 1 there because we're doing our X gate. And while qubit 1 is remaining the same. And similarly, we are flipping qubit 0 from 1 to 0, and our qubit 1 is remaining in the 1 state. So all you need to do is change your qubit 0 and make no changes to your qubit 1. Cool. So similarly, to create our, I guess, 1 state, we're going to encode that to be our phi minus state. So it is the same parity as our phi plus state, but opposite phase. So we have our minus sign here. And to get the minus sign, we need to do a Z gate, also called a phase gate. The names start making sense when you see how they're used, hopefully. So all we're doing is we're adding a minus phase to our 1 state, and we only need to add this phase to one of the qubits, and this is perfectly fine for getting this net phase. And then the final state, our psi minus state, technically minus psi minus state, this is a global phase here, so we ignore it in the end. We're perfectly happy with this result. We actually end up doing an X gate and then a Z gate to encode this 3 message, this 1-1 message. So we'll get to that in the optional content a bit after time, because it looks like we're going a bit over. But I'll try to get through the majority of this before we make time. So again, this is just noting the indexing again. This is Alice's qubit, qubit 0, and this is Bob's qubit, qubit 1. So Alice here and Bob here. So if we want to create our circuit from scratch every time we create one of these 4 Bell states, it's a bit annoying if we're sending many bits of information, even though we are getting 2 bits for the price of 1. But what we want to do is write a function that will make any of the 4 states for us, depending on what we put in. So if we say, I want to create 0 state, then it will create the correct state. One important thing is that all of these states do begin with a Hadamard gate and then a C0 to create our initial phi plus Bell state. And then we add our additional gates to create our other Bell state options. So this first function here, create Bell pair, is the kind of common part of the 4 circuits. This is also what's done by Charlie in many protocols. And then the second function that we're going to create is going to be the, I guess, state dependent portion. And that's going to actually take in a parameter that the function changes based on this. So the variable we're passing in this case, QC, is a quantum circuit instance. So we've already initialized a Qiskit quantum circuit. And then we're just applying these gates to the circuit we've already created. So I'm going to initialize this function, and we'll use it in a bit. And then we're going to take our second function, which we'll call specify state. And this will have 2 inputs, our quantum circuit and the message we're trying to encode. So the message we're trying to encode is one of these 4 numbers, 0, 1, 2, or 3. And then we can encode the, we will add an additional gate to our sequence dependent on what our message is. So if our message is 0, 0, we're going to do nothing. This pass function means we do nothing. 0, 1 is our Z gate. So 0, 1 is the same as our phi minus state. 1, 0 is our psi plus state, and so we do an X gate to do our bit flip. And then 1, 1 is our psi minus state. So we're going to do an X and then a Z gate. So we flip both our parity and our phase. So you can think of this as the X gate being a parity flip and the Z gate being a phase flip. And we have this written backwards. But I'll just change how this is noted. Okay. And then if it's not one of these four strings, then it's invalid. And we will just print an error message and not actually change the state. Okay, so we've now initialized this function as well. And so to test this out, we're going to create a quantum circuit, put this quantum circuit into a bell pair. And then we're going to add a barrier, which is not like a physical thing. It's just a visual aid in Qiskit's visualization software that allows us to see where the separation between the sequence is. So in our like Charlie-less sequence, this was our travel step where Alice and Bob travel far away from each other. And then we're going to encode our state. So in this case, this is actually a psi minus state. I'm going to put this as a, I guess, psi plus state, which is 1, 0. And so what we're going to do is run this, and you'll see this is our Bell state preparation here, our Hadamard, and then our C0. And so this is what Charlie has done, or what Alice and Bob did while together. We have our barrier, which is where either Charlie sends qubit 0 to Alice and qubit 1 to Bob, or where Alice goes home and Bob goes home. And then we have our actual gate sequence, our encoding for our state. So Alice does an X gate on her qubit. So now the, I guess, kind of, well, second to final step is transmission, where Alice just sends her qubit to Bob. And so Bob will then have 2 qubits again, and he can decode the state he got. So the final step of superdense coding is actually decoding your qubits. So you need to do kind of the inverse gate sequence. So I guess, can you guys guess what the if we're trying to inverse or do the inverse of what we started with, what gate sequence can you guess we would want? And you guys are having a debate on tautology in the chat. But does anyone know or can anyone guess? You don't have to know anything, but can you guess what the inverse of our gate sequence would be? What Bob might want to do to retrieve Alice's state. Nice. Zena, you were right on. We want a C0 and then a Hadamard gate. So the inverse of our starting bit. So we want to remove the effects of the circuit we started with. So there's a lot of like verbose stuff here. But we remember, if we have our phi plus and our phi minus states give the outputs 0, 0 and 1, 1 with probability 50, 50. So we need to be able to distinguish both our phase and our bit values. So when we encoded our states, we applied a Hadamard gate and then a C0. And the Hadamard gate is our superposition gate, while our C0 puts us into is our entangling gate and puts us into our superposition state. So we want to undo the common part of the circuit and just do a C0 and then a Hadamard. So we're functionally unentangling our qubits by doing the C0, and then we are I guess we are projecting from I think the best way to think of a Hadamard gate is going from your equator of your block sphere up or down to the poles or the 0 or 1 state of your block sphere. So you're moving your phase information into the energy basis. So if you are in the plus state, a Hadamard gate will bring you up. If you're in the minus state, it will bring you down. I think that's the right ordering. But depending on which phase you have, you will be distributed, or you will have your state end up in an energy state that distinguishes these two phases. So I'm sorry if this is a bit confusing verbally. I think it makes, like, it has some intuitive sense. So our measurement circuit, like a bell measurement, which you might hear about, is a C0 gate or a CX gate, and then a Hadamard gate. So we're going to define our bell measurement circuit. And then we can do a sequence of gates, I guess, or like we can write out the results of our sequence of gates. So if Bob receives a phi plus state, and you do a C0 on it, you're functionally unentangling the state, because now if qubit, regardless of what qubit, what state Alice's qubit, which is this 0th qubit, the rightmost qubit, regardless of what state Alice's qubit is in, Bob's state, or Bob's qubit is always in the 0 state. So that means it's not entangled. The state of one qubit does not tell you what the state of the other qubit is. So this is our, this is, I guess, like, it's not quite a plus state. It's a plus state on Alice's qubit, and just like a 0 state on Bob's qubit. So if you do a Hadamard gate, Bob's qubit isn't going anywhere, so you're doing a Hadamard gate just on Alice's qubit. So Bob's qubit shouldn't go anywhere. Bob's qubit's just hanging out in its 0 state. But Alice's qubit will be rotated from the plus state up to pointing up on the block sphere. And you can visualize that with like this. You can make like little block sphere animations if you want in Qiskit, or I believe I've done them in Qtip more, I think, but they're pretty fun. And then after this Hadamard gate, you'll be in the 0-0 state. And so that will give you the exact state you expect when you measure it classically. Same way, if you are in the psi plus state and you apply a C0 gate, Bob's qubit will just end up in the 1 state, while Alice's qubit will be in a superposition of 0 and 1. If you do a Hadamard gate, because Alice's state is in the plus state, a Hadamard will result in Alice's qubit going to the 0 state, and the Hadamard is being applied just to Alice's qubit, so Bob's qubit will remain the same in the 1 state. And then your classical bits will just be 1, 0, because they'll be the exact same as your quantum state, because they're both in a single energy basis state, not a superposition. Now, if Bob receives a phi minus state, which is our 0, 0, minus 1, 1, and you apply a C0, you're again unentangling the state. Bob's state, or Bob's qubit, will just be in the 0 state no matter what Alice's qubit is doing, while Alice's qubit is now in the minus state, so it's 0 minus 1. And so once you apply the Hadamard gate to Alice's qubit, Bob's qubit will remain in the same state, while Alice's qubit, because it's in the minus state, it will be rotated down to the bottom of the block sphere, or the 1 state. And then you can measure this quantum state, and you get your classical bits 0, 1. So did that make some sense to people? Because this is kind of like the important mathematical part, and you can definitely work through this by hand if it's not. I'm not going to say it's not like difficult, but it's not terribly complicated, because it's just like 4 bits, or 4, like a 1x4 matrix. Cool. Okay, I'm not getting questions. You guys, hopefully you guys are doing okay. You guys seem very concerned by Bob, but Bob got the right answer. So that's good. So now we are a bit over. I'm sorry. Like, of course, I always say, like, if you guys need to leave, always do. Don't feel bad like leaving early or leaving on time. This will be uploaded. So the final step is just put together all of our functions. So we create our quantum circuit. We can create a bell pair for this circuit. We'll put a barrier in the way just as our visual aid. We'll decide our message, then encode it with our specify state function. We'll add another barrier just so we know when that's happened. And then we'll do our measurement function and we can draw our final state with that. This is our final circuit. This first bit is what Charlie is doing. He's creating the bell state. The second section is what Alice is doing. She's encoding which bell state we want. And then this final bit is what Bob is doing. He's measuring the bell state with a CNOT and then a Hadamard and then measurement operations that project your qubit state onto a classical bit. So now we can run a simulation to see if Bob gets the right message. And I was told this sometimes takes a while, but it seems to be fine. You can see Bob with the calculator got the 0-1 state with almost 100% probability, or pretty much 100% probability. So that's really, really good. That's a very convenient result that everything works perfectly fine. So was mentioned that quantum teleportation is a very similar protocol to superdense coding. And it is important to avoid confusion between the two. So with superdense coding, you're transmitting 2 classical bits using 1 qubit. You're transferring 1 qubit, but you are using a bell pair. Meanwhile, quantum teleportation is transmitting 1 qubit state based on 2 classical bits. Both of these do use 2 classical bits and 1 bell pair of 2 qubits. And the quantum teleportation it's not cloning, it's not actually teleporting the qubit, but it is recreating our qubit state at a different location. This is, I guess, it's not cloning. It is destroying one state and creating the other. So you can't have them existing simultaneously. Cool. So, and this protocol is pretty much the same thing, except Alice and Bob are swapping what they're doing pretty much. And this will be part of your problem set for this week. Okay, so this is the end of the required content. I will start a post Zoom poll. Let me know how much this was understandable. And of course, if you already needed to go, you're gone, but feel free to go, but I will go through how to create the final bell state in a little bit more detail now. Did we do anything that we didn't do in lecture? I don't believe so. This is a pretty complicated, or it's not like a super complicated protocol, but it's a little hard to wrap your head around. And so this is us just implementing it in Qiskit. But just to give a kind of final view of what we did, is we allowed Alice to send Bob a 2-bit message by transferring only 1 qubit, by using a bell pair, an entangled pair of 2 qubits. Oh, and I got a question from Jonathan. How is it that in particles and field all particles have 6 parameters, 3 for position, 3 for momenta, and fields have infinite parameters, or is that only classical theory? So in general, quantum mechanics and like quantum information tends to not use vectors. Like we don't care about the position of our qubits generally. Like we don't use position eigenstates or momentum eigenstates for our qubits, because that's very hard to control super well. Like we do have to control it to minimize noise, but we generally just use the energy eigenstates because we can control them and read them out better. It's like much higher precision than we can position or momenta. So we're not using vector parameters, we're using scalar parameters because energy is just a scalar. So it depends how you define parameters, I guess. Momentum and position are conjugate pairs. Similarly, so if you don't, a conjugate pair is like one is the Fourier transform of the other. If you don't know what a Fourier transform is, then I recommend taking like differential equations, a signals course. I don't remember what covered Fourier transforms originally for me. Maybe calculus. It just the idea of a Fourier transform is taking an integral over a particular state and like multiplied by an exponential that transforms your state from one from one thing to another, and the things you transform into are generally conjugate pairs. So like you'll transform something that depends on position by e to the I like x to e to the ik x and sum over all your x's, like your integral will take you over all your x's, and then you'll get the same parameter in terms of k, which is your momenta. Similarly, for energy, time is your conjugate pair. So we can very easily create very precise frequencies. Not very easily, it's been a century of work to do this. But those are your conjugate pairs in this case. Yeah, cool. Okay, so now with our, I guess, final section. Oh, we do have further reading down here. And there's like some nice videos on superdense coding by Michael Nielsen, who wrote Quantum Computation, Quantum Information, which is like the best book on quantum computing, in most people's opinion. I mean, it's not like best is a strong word, but it's a very, very good book. There's also a really good QxQ textbook page on superdense coding. This has the really nice little table on how to create these different states. And then there have been experimental demonstrations of quantum teleportation. It's funny, like it's actually like just kind of ridiculous. Like this is like from '97. I believe this is Dirk Baumeister, not Dick Baumeister. But he's now a professor. Originally, he was at University of Santa Barbara, and now he's at University of Chicago. John Wei Pan runs like 100+ person research group in China. Klaus Madel and Manfred Ebel, I don't know, or Harald Weinfurter, but Anton Zillinger is what the GHZ state is named after. So it's a fun paper. It's very like dense, but there's a lot of like big names, I guess, that were involved with the like quantum teleportation is considered very important. And so if you want to be a big professor in quantum, showing teleportation is a good way of doing it. Maybe not anymore because it's been done, but it's still like it was a big deal. Okay, so the last bit is preparing our psi minus state, which is our 0, 1, -1, 0 state. So it's a odd parity state and a pi phase between the two like superposition states. So to do this, it's really like it's fairly simple. We need to do both a parity flip. So we want to flip, I guess this says qubit 1, this should be qubit 0. Qubit 0, and the Z gate to flip the sign of the circuit. So that's all we're doing is just the second, we're doing both of our state preparation steps rather than just one. And so we could put like a barrier in between each of these if we wanted to. I guess I can try. I feel like I'm going to mess it up. I feel like whenever I try to type anything out in labs, I like don't do it quite right. But these are our 3 steps, where we have Charlie's part doing a Hadamard and then a C0 to create our bell pair. We have Alice's part doing our X and our Z gate, so our parity flip or our bit flip, and then our like phase flip, or our, I think it's just a phase flip. I don't have a fun other name for it. There's a pi phase rotation, if you prefer. And then we have our measurement. We actually do need to have our, we shouldn't have a barrier here because we don't actually have Bob doing it yet. So we would need to have, like, this is just to check what state we created. So here is the same code as we had earlier to check this state. And you can see we have a little over 50% in the 1-0 state and a little under 50 in the 0-1 state, but we still don't know what the sign of the state is. So you can use a state vector simulator for this. So the final bit is you can load this onto the quantum computer. It will take you like a few hours to run this. But this is how you do it. And I'm just going to run through it. I'm not going to actually queue the job. But you want to import your like IBM Q, which is like your account information for the IBM quantum experience that allows you, like, it gives you like the keys necessary to send a job to the quantum computer. And then you're going to import from the IBM Q providers. In this case, we're just going to take the least busy simulator available, the least busy computer available. And then we'll load our account information, choose the provider that is least busy, or take our provider from IBM Q first, and then choose the least busy. We do need at least 2 qubits, so that's what this configuration means. Is we're trying to filter for a lambda function is just kind of an inline function. It's a pretty common computer science term, but if you're not familiar with it, don't worry about it. But we're taking a lambda like X function and calling configuration for that and the number of qubits like in our configuration. We just want to make sure we have at least 2 of them. Similarly, with this lambda, we're taking the configuration and making sure it's not a simulator, because IBM Q hosts both classical simulators and actual quantum computers. And if it's a simulator, the simulator flag will be set. And this final bit is making sure that our quantum computer is actually running. So there's another flag called operational, and we just check if it is operational, if operational is equal to true. And that's all we're doing. And then we run our circuit, where we pass in our circuit, we pass in the backend that we've chosen, which that's where the least busy provider we searched for was stored. And then we have our 256 shots here. So we can't, like, I have it run in history, but I'm not going to run it now. You can check the status of your job. And then once it's finished, we can review the results, pull out the results from the job, and then plot the histogram. And you can see it's not as beautifully perfect as it was in like a real or in our simulator, but we did get 89% of our shots resulted in the 1-1 state, which is the one we were trying to prepare. That's what the psi minus state encodes to. And only, I guess, 6.2% was in the 1-0 state, and 5.1% was in the 0-1 state. And again, this is just because of errors in our quantum computer, noise, etc. What you'd often like the actual like term we normally use for this in quantum computers, I just want to drop, is called fidelity. So this, you would say like I guess in this case, it is a more complicated circuit, so I wouldn't call this just state preparation. But like, I guess like your state preparation measurement error, or your state preparation measurement fidelity is maybe like 88.7%. A lot of times you'll quote a single gate fidelity. So your single qubit gate might be like 99%. Your 2-qubit gate, like your C0, might be 95%. And then your readout, like your measurement operation, might be 90%. And you add them all together, you add all those errors together, and you get a total sequence that's maybe on the order, like 88.7% is pretty solid, honestly. And then you could do error correction to try to improve this. Yeah, cool. So you can see that there are other results, and you can print like this accuracy metric for this, because this is a full gate sequence. It's not just like a single like gate like characterization. Like normally you talk about fidelity with regard to a single operation, but our total circuit resulted in an 88.67 accuracy results. So with that, that is all the content for this lab. Are there any final questions? I know we're quite over time, but I think, or I hope things went pretty well. And this all made like some sense. I think I prefer to go through things more slowly and like make sure I'm getting through all the questions. Okay, well, if there aren't any final questions, I hope you guys all have a wonderful week. And I'll see you next week at week, I guess, 19 of the lab. We're going to do more quantum protocols. The rest of the semester in general will be mostly quantum protocols, and then we're going to get into some more experimental stuff later on. We'll learn more about this fidelity metric and how like actually running on a quantum computer gets these results. So cool. Thank you, everyone. I hope this lab was useful. I'll see you next week. Bye.